This is video 17. In this video, we formalize and prove the remarks of the previous video. We start by analyzing the running example of this video. Consider a simple B-infinite window W which is not a cycle. This window is in gray. The graphs G1 and G2 are the cut of the grid associated to this window. Consider a path P such that its first and last positions belong to the window W. Note that P is not extremum. Here is the decomposition of the path P in extremum arcs in graph 1. Arcs A1 and A2 are negative while arcs A3 and A4 are positive. Here are the interiors of the different arcs of the decomposition. Here is the window W' and the cut of the grid G3 and G4 associated to the decomposition. Here is the dual decomposition of the window W associated to the decomposition. Here is the interior of the first dual segment. Here is the interior of the second dual segment. Here is the interior of the third dual segment. Here is the extremum path extracted from the path P. Here is the window W second and the cut of the grid G5 and G6 associated to the path P. The graph G6 is the right side of the dual segment D0 and D4. Now we prove a preliminary result. If a position belongs to two different interiors, then it also belongs to the path P. We will list here the different possible cases. A detailed proof is written in the article available online. We will work using the window W' and its cut of the grid. Here W' is in gray, the path P is in white and the dual segment D2 is hatched. We remind that the path P is a subgraph of G4, then the interiors of the different dual segments are subgraphs of G4. Now we consider the dual segment D2. This dual segment is a segment of the window W'. Consider the basic segment of P associated to the dual segment D2. In our example, this is the segment of P from index 1 to index 80. Now remark that the position P1 is the first position of the dual segment D2 and the position P80 is the last position of the dual segment D2. Then, we need to switch the direction of this segment. Indeed, by definition, the interior of a dual segment is always the right side of the window of the interior. Thus we consider the following path Q. The window of the interior of the dual segment D2 is the concatenation of D2 and Q. The interior of D2 is the right side of D2 and Q. Now we consider the extremum arc of G4 extracted from Q. Q is in white and this extremum arc is the segment of Q from 1 to 39. This segment is hatched. Let's focus on the interior of this extremum arc. Here the window W' is in white. The interior of the extremum segment is hatched, and its window is in gray. The extremum arc extracted from Q and the dual segment D2 are segments of this window. The interior of this window also contains the segment of Q from index 1 to index 1 and the segment of Q from index 39 to index 80. Then, the interior of D2 is a subgraph of this graph. Now, we do the same reasoning for the dual segment D3. We obtain an extremum path Q' of G4. Three kinds of cases may occur. Either Q' dominates Q or Q' is consecutive to Q or Q' intersects with Q. In the last case P is not simple, which is a contradiction. Here we study the case where Q' is strictly consecutive to Q. Since P is simple, then the interiors of these two extremum arcs does not intersect. Thus the interior of the dual segment D2 and the interior of the dual segment D3 does not intersect. Note that there exists a special case. Here Q' is strictly consecutive to Q, but if the arc A2 is of length 1 then Q' is consecutive to Q and they share a common position. This position is the unique position of the arc A2 and thus it also belongs to the path P. Thus the lemma stays true in this case. See the article for more details. Now, we still consider the dual segment D2 and the extremum arc extracted from the path Q. But we do the same reasoning with the dual segment D1. We obtain the following extremum RQ2. The interior of Q2 contains the interior of the dual segment D1. Moreover, this path is dominated by Q. Then consider the segment of Q from 39 to 80. This segment dominates Q2. In fact, in this example, Q2 is a subgraph of this segment, but they do not have the same direction. In this case, the interior of Q2 is on the left side of Q and thus does not belong to the interior of Q. In this case, if a position belongs to both the interior of the dual segment D2 and to the interior of Q2, then it belongs to Q2 and thus to path P. Now we deal with the interior of the dual segment E0. This graph is the graph G6 and it is also the interior of the dual segment D4. Remark that the extremum path extracted from P is an extremum arc of G4. In this case, this arc is positive and the graph G6 is the right side of this arc. Thus the positions of this arc are the only positions which belong to both the interior of this arc and to the graph G6. Now consider the arc Q2. This arc is dominated by the extremum arc extracted from P. Thus any position which belongs to both the interior of Q2 and to the graph G6 also belongs to the extremum arc extracted from P. In our example, there are no such positions. Now we analyze the movement of a path Q which does not intersect with P. The previous result implies that the path Q has to intersect with a dual segment in order to enter or to leave its interior. Here we consider that the first position of Q is in the interior of D1 and that the last position of Q is in the interior of D2. Our aim is to find either an arc of G1 which dominates the arc A2 and is a subgraph of Q, or an arc of G4 which starts in D0, ends in D4 and is a subgraph of Q. We will also work with the window W'. Now in order to leave the interior of the dual segment D1, the path Q intersects with D1. Let K1 be the index of this first intersection. In order to enter in the interior of the dual segment D2, the segment of Q from K1 to its last position has to intersect with the dual segment D2. Let K4 be the index such the position of Q at index QK4 intersects with D2. Since the index K4 is correctly defined, we can consider the index K3 as the first index such that the path Q at index K3 belongs to either D2 or D3 or D4. In our example, it belongs to D4. Now we consider the index K2 as the maximum index lower than K3 such that the path Q at index K2 belongs to either D0 or D1. In our example, it belongs to D0. This index is correctly defined since K1 is correctly defined. According to these definitions, the segment of Q from index K2 to index K3 is either an elementary arc of either G3 or an elementary arc of G4. If this segment of Q is an elementary arc of G3, then it is also an arc of G1 which dominates the arc A2. If this arc is an elementary arc of G4, then in our example, this path starts in D0 and ends in D4, then this elementary arc dominates the path P in G4. Now suppose that the position of Q at index K3 belongs to the dual segment D3. In this case, the elementary arc intersects with P, which is a contradiction. Thus a path Q which starts in the interior of D1 and ends in the interior of D2 either dominates the arc A2 or dominates the path P in G4.